Hi, my name is Cooper Quintin, and today we're going to talk about detecting 4G base stations in real time. I am a little bit about myself. I am a senior security researcher with the Electronic Frontier Foundation. I have a toddler and a newborn, so you'll have to forgive the dad jokes and the bags under my eyes. And I'm a former teenage phone freak, which might explain why I got into the work that I'm doing. If you're not familiar with EFF, we are a member-supported nonprofit. We defend civil liberties as they intersect with technology. So we think that your rights to freedom of expression and your right to privacy come with you online and come with you when you're working with technology, as well as in the so-called real world. And we've been doing this work for 30 years. And specifically, I work in the threat lab at EFF, and I'll talk a little bit more about that in a second. But first, I want to take a second to thank my colleague Yamna. This is as much her work as mine, and although she can't be here to present this with me, this is really her project too, and I want to thank her a lot. And if you liked the work that we did, check her out on Twitter at RivalElf. So what is Threat Lab? Threat Lab is the division of EFF that looks at technology that specifically targets at-risk people. By at-risk people, I mean activists, human rights defenders, journalists, domestic abuse victims, immigrants, sex workers, minority groups, political dissidents, etc. And the goals of this technology are often to gather intelligence on opposition or on dissident groups, to spy extraterritorially when people have left your country and you can no longer spy on them through traditional means, to locate and capture people, to harass them, and overall, generally, to stifle people's freedom of expression and prevent them from doing the work that they do. So typically at Threat Lab, we look at things like state-sponsored malware or applications that spy on people, and we have a couple of reports out about that you can check out on the EFF website. But today, I'm going to talk about a different project that we worked on around cell site simulators. And first, let's talk about what is a cell site simulator. A cell site simulator is generally a transmitter and or receiver that intercepts metadata from cellular phones, often by masquerading as a legitimate cell tower. It also goes by the name IMSI catchers, Stingray, Hailstorm, or fake base station. And for the purposes of this talk, we will use all of those terms interchangeably. And they can all be considered to mean basically the same thing. So we first got interested in detecting cell site simulators around November of 2018. When we started getting messages from people out at the Standing Rock protests against the Dakota Access Pipeline in North Dakota. This was an oil pipeline that was being built through Indian land, and there was a movement to stop the pipeline from being built. Some of the activists out there had begun noticing strange things going on with their cellular connections and had downloaded some apps which purported to be able to detect cell site simulators. They got some readings from those apps and sent them to us at EFF. And we thought that they were interesting enough that we might as well go out and take a look and see what we could find. If we could find evidence of police using cell site simulators against Standing Rock protesters, that would be a pretty big deal. So I packed a bag and downloaded some of these cell site simulator detector apps onto my phone and brought a couple of cheap software-defined radios, and away I went. And when I got to Standing Rock, I started looking around. I fired up the apps and fired up the software-defined radios. And what I pretty quickly figured out was that I have no idea what I'm doing. It turns out that a lot of the apps have a problem with false positives. I was getting a lot of readings, but I couldn't be sure if those readings meant there was actually a cell site simulator around, or if it was just the cell network doing the strange things that happen when it fails or gets overloaded. Because we were in a pretty remote area, those were certainly, with suddenly a lot of people in it, those were certainly possibilities. And I had no idea what I was doing with the software-defined radios. I was recording Spectrum, but I really didn't know what to do with those recordings. After consulting with some friends from the University of Washington, what we figured out was that there wasn't actually any 2G GSM signal anywhere in the area at all. Now, this was an interesting find and pretty important. Why was it important? it's important because of something called the Stingray. The Stingray is probably the most well-known example of an IMSI catcher or cell site simulator. The Stingray operates natively on 2G and has the capability of tracking people's locations, figuring out who's in an area, and purportedly can also get metadata about who's calling who. But we know that the Stingray operates by impersonating legitimate 2G towers in the area. Since there was no 2G signal at all anywhere in the area, we know that a Stingray couldn't have been involved because there were no 2G signal, legitimate or illegitimate. This also meant that the apps that I was using, which are designed to detect the heuristics that a Stingray gives off, they're designed to detect the things that a Stingray does, probably wouldn't work. Because if a cell site simulator was being used out there, it would have to be a next generation cell site simulator, which was operating natively on 4G. And at this point, we had no idea how those worked. So I came back to EFF with a goal in mind. I wanted to figure out exactly how a 4G LTE cell site simulator could work. We knew that the nearby city of Oakland had just bought one called the Hailstorm that purported to work natively on 4G LTE. And this is interesting because as much as we knew about how the previous generation of cell site simulators worked, such as the Stingray, as far as we knew, all of those vulnerabilities had been fixed by 4G. So how could a 4G cell site simulator possibly work? We decided to take a look at the academia and ended up doing a deep dive into all of the available literature on 4G vulnerabilities for the next year or so. And out of that came a really excellent paper that Yamna wrote called Gotta Catch 'Em All, which summarizes all of the vulnerabilities that next-gen CSSs could be taking advantage of in a very readable and understandable way. And I'm not going to dive into that here because Yamna already did an excellent job and gave a talk in Enigma last year about her work. And if you're interested, you should go read the paper. But as a high level, all of the vulnerabilities happen when the phone first connects to the tower, before it authenticates that the tower is a legitimate tower owned by the phone company. And that's where all of the attacks that a 4G cell site simulator can do might happen. Luckily for us, that's an area that can also be easily replicated in software, which we'll get to later. So now that we had a good idea of how 4G cell site simulators work, the next thing we wanted to know is how often are they being used? Well, we know that law enforcement uses cell site simulators quite a lot, and we can find out how often they use them from Freedom of Information requests. Luckily, there's been several requests filed by the ACLU and other folks, which give us a pretty good picture. From a ACLU FOIA request, which was published earlier this year, we found out that ICE and DHS use their cell site simulators hundreds of times per year, somewhere on the order of 200 to 300 times per year. Not to be outdone, though, local law enforcement also uses their cell site simulators quite a bit. Santa Barbara Police Department used their cell site simulator 231 times in 2017 alone. But in contrast to that, the Oakland Police Department only used their cell site simulator between 1 and 3 times over the course of 2017, 2018, and 2019. So what accounts for this discrepancy? Well, we think that because Oakland has strong privacy laws and strong community control of police or CCOPS ordinances, we think that for that reason, Oakland has been much more restrained about their use of cell site simulators, whereas Santa Barbara PD has not had that issue. So this shows to us that CCOPS ordinances actually work quite well. But unfortunately, not everybody responds to FOIA requests. Foreign spies, for example, are using IMSI catchers in and around Washington, D.C., and presumably in other places in the U.S. and around the world. We know this from a report put out by the Department of Homeland Security. We also know that cyber mercenaries like to use IMSI catchers, thanks to a report from NSO Group thanks to a report from Amnesty International about how NSO Group had been using them to spy on a Moroccan journalist. We also suspect that criminals are using IMSI catchers, such as cartels in Mexico. And it makes sense. IMSI catchers or cell site simulators can be built for as little as a few hundred or $1,000 or $2,000. And this is certainly within the budget of any well-funded or even meagerly funded criminal group. So, since not everybody can be FOIA'd to find out how widespread of a problem cell site simulators are, we also need to work on detection. There are two schools of thought of people working on detection of cell site simulators. The first is app-based, such as Android IMSI Catcher Detector or AIM-SIC-D and Snoop Snitch. The advantages of these are that they're cheap and easy to use. You just have to have a phone and download a free app, and then you're good to go. The disadvantages are that you get a limited amount of data. You can only get information about what towers the phone has connected to. And you can only get the information that the phone's and operating system's API will give you. So because of this, you get a lot of false positives and a lot of false negatives. A lot of the things that the phone system does when it fails or when somebody makes a mistake look very similar to the things that a cell site simulator does. The other school of thought on this is radio-based. This is things like Seaglass from the University of Washington or SITCH from Ash Wilson. The advantages of these are that you get better data and lower level information. You can get information about all of the towers in an area by using a software-defined radio, not just the ones that your phone is connected to. And you don't have to worry about the API of the phone and what data it will give you. The disadvantages of these are that they can be harder to set up and use, and the data can be harder to interpret. You have to have some programming knowledge and some database knowledge, and you have to buy hardware, usually a software-defined radio and a Raspberry Pi and such. So we wanted to answer the question, can we detect 4G using cell site simulators using similar efforts? Well, we like the radio efforts because we can get lower level data. And we can see all of the transmitters, not just the ones that we're connecting to, and we can compare that data over time. But all of the previous efforts have one big weakness. They're looking at stingrays. They're looking at 2G and the heuristics that we know to be viable for a stingray. But we wanted to look specifically at 4G transmitters, and we wanted to look specifically for heuristics that we think 4G cell site simulators might be using. And furthermore, we want to verify the results. We want to be able to actually track something down and see if it's a cell site simulator or just an antenna behaving poorly. So we built a thing we call Crocodile Hunter. Crocodile Hunter is a software and hardware stack. All of the software is open source. Its backend is based on SRSLTE, which is an open source LTE software stack, which emulates everything from the base station to the mobile phone. It communicates with the front end over a local socket. The front end is written in Python and handles the heuristics, deciding whether something is suspicious or not, the database, and the user interface. It gets data from SRSLTE, adds it to the database, runs some calculations, and displays tower locations. We also have an API for researchers to be able to share data with us. This is the hardware setup. As you can see, it's pretty compact. We have a software-defined radio, a couple of antennas, a GPS antenna, and of course a laptop or Raspberry Pi. So it can all fit easily into a backpack or a car discreetly. This is a test run that we did in downtown San Francisco during the Dreamforce conference in January of 2019. January of 2020. This was so each of these points on the map is a cellular base station that is transmitting. And probably many of these points are multiple antennas connected on one base station. Each of the skulls are also base stations, but they are ones that we find suspicious. Clearly, not each of these is going to be an IMSI catcher, which is why we need to track them down and see what they are in person. So that's the front end. And then the back end, we can see that SRSLTE scans a list of frequencies for the information blocks which are transmitted by the cell tower. and then decodes those information blocks, which contains things like the cell ID and the and other important identifying features, and sends them over the socket to the front end. And then we use a method called trilateration and some radio physics. We can map out where all of the base stations are located in real time. This is a rough estimate, and it's usually off by a couple of meters. But it's close enough that we can compare it to a public open source database of cell tower locations, such as Wiggle or OpenCellID, to see if this transmitter has a history of transmitting in that area, if it's what we expect, or if it's something new that has just come up in the last few days. And then finally, we look for anomalies. And this is things like base stations that are moving, or base stations that change signal strength, base stations that aren't where they should be, or base stations that have just shown up, base stations that are missing parameters, or new base stations. And just because we found an anomaly doesn't mean a cell site simulator. That's why we have to verify it in person. Using the location that we have, we can actually track it down. If it's on top of an existing cell tower, great, it's probably legit. If it's in the back of an unmarked van, well, that would be very suspicious. So what have we found so far? One of the first things we found during a test in Washington, D.C. was a couple of very suspicious base stations. We had two base stations, which were both transmitting a country code and network code shown here of 310 and 410. This is the country code and network code, respectively, for the USA and AT&T. This is what we would expect to see. But suddenly, that base station started transmitting with the same base station ID of 654794, indicating that it's the same base station, suddenly started transmitting a country code and network code of 308 and 451, which do not belong to any 308 does not belong in the US, and 451 doesn't belong to any network in the US or anywhere in the world for that matter. A different base station suddenly started with the same base station ID again of 653671, broadcasting a country code and network code of 350 and 490, which corresponds to the island of St. Pierre and Miquelon in the country code, which is just off the coast of Nova Scotia, and 490, which isn't used by any network, again, any network anywhere in the US. So we found this very suspicious. This actually isn't something that we expected to find. This isn't a heuristic we expected to see. So we weren't really sure what to make of it, and unfortunately, we didn't get to track it down at that point. I would have chalked it up to just a malfunction, but later, a few months later, I was in Oakland, California, running some scans again during a large protest on June 19th, or the Juneteenth celebration, which was taking place in the form of a march from the port of Oakland to downtown Oakland. And what we saw that time was, again, some very suspicious base stations, broadcasting, once again, country codes and network codes, seen here under the PLMN category, that don't belong in the US. We saw one broadcasting a country code of 213688, another one 31959, and another one of 710738, which don't correspond to any country codes in the US or any network codes in the countries that they do belong to. So this is, again, very suspicious. We don't quite know what to make of it, but it certainly indicates that something weird is going on. This is not something that we normally see in our menu tests, but it is something that seems to crop up at certain times when other things are happening. We're not sure what to make of this, and further studies are needed. Finally, what's with the name? Well, like I said, a Stingray is the most widely known form of a cell site simulator. And a Stingray is also what killed the great naturalist Steve Irwin. So we named, also known as the Crocodile Hunter. So we named this project Crocodile Hunter to pay our respects to Steve. Finally, future work. We have ongoing tests in Latin America with the FADE project in Washington, D.C., in New York City, and hopefully soon in your town, because this project is open source and we want you to set it up too. We want to get more data so we can better understand how IMSI catchers work, and we want to make improvements to our heuristics. Finally, how can we stop cell site simulators? There's unfortunately not much we can do to protect ourselves individually, and 5G doesn't solve the problem. We would like to see 2G support be dropped on iOS and Android. We would like to make some changes to the protocol, such as eliminating the pre-authentication messages. And there's some great papers out about how we can do that. We need more data, we need stronger privacy regulations, and most importantly, we need the companies and standards organizations to actually care about this problem and take it seriously. The key takeaways here, we have a pretty good understanding of the vulnerabilities in 4G, which commercial cell site simulators might exploit. None of the previous IMSI catcher detector apps really do the job anymore, but we've proven that the same principles which worked on those should work on next generation cell site simulators as well. And finally, the problems of CSS abuse can be solved, but it's going to take a lot of political work and a little bit of engineering. Thank you for your time. Again, my name is Cooper Quintin. I'm a senior security researcher, and you can reach me at cooperq@eff.org or on Twitter @cooperq. Enjoy the conference.